Hello, everyone. I hope everyone's doing as good as you can given these circumstances. So this is the first of the video lectures here. So this typed up document here is along with this video if you want to like go through it as well. If not, I hope it helps. So this is all about double integrals, and if you have not done so, I hope please watch that video that I sent that was the Friday's lecture, because that's gonna give how this all relates back to Calc 1, because the notation is gonna look rough, but don't worry, it'll be just like in Calc 1. Like after you've done the Riemann sums and all that stuff, then you just learned how to do the integrals, and you haven't really had to do it much anymore. So don't worry about it. It's just going to look a little bad here in the beginning, but it's going to be eventually super mellow. Okay, so first, so what is going on here in this setup? So what is a double integral? Let me draw a picture to go along with what's about to happen. All right, so so here's x, here's y axis. All right, you have a, you have b. Interval AB. Here you have C. Here you have D. All right. Okay, so this little rectangle here is what the integrals are going to be over. So where just an arbitrary interval or rectangle. So what does this look like in 3D? So we're talking about and now I'm learning that. All right, here we go. Okay, so XYZ axis. All right, so here's A, here's B, and then here was C, and here was D. All right, so the rectangle was out here somewhere. All right. Okay, so that's on the ground. All right, up above is the surface. So the surface is somewhere up here. Say, let's cut it right here. All right, so the surface is in the air. This would be the f of x, y. All right, so underneath this is this rectangle, and you want to trail it up. All right, so when the projection of the surface down on the ground is what's on the rectangle, but what we're going to eventually be computing is the volume of what's underneath the surface. So I'm just trying to give an overview of all this fancy stuff on the handout, so that we're going to just basically overlook it all, and I'm just going to talk get from this picture. This is everything. So on the ground here, this is what's on all these. That's going to be this thing R. So R is just some subset of R2, and that's it. And so then that's what's on the ground floor. The surface is in the air, and then what eventually we're going to do is compute the volume of this piece that I've kind of shaded in here. And so, and how do you compute volume? It's got to be area of this times that height. The height is going to be f of x, y, and then the area is just something down below, which is computed always, just an area of a rectangle, length times width. So the volume of this whole thing is length times width multiplied by the height, but the height is given by a function. So that's why when you look at this over here, in this complicated looking thing, what's just forget all the rest of this stuff, but what's going on is this right here is the height. That thing right there is going to be the that's the area on the ground. So that over here, that's why you have this term right here. That's the length times the width. That's the height at some kind of test point or whatever, and then you're going to take m and n to infinity so that it fills out the picture. What you're doing is approximating this area via a whole bunch of tiny little rectangles until you've filled out so many tiny little rectangles it fills up the whole thing, and then that's how you pick up what the integral is. And so, like I mentioned, what this is going to be, this is the volume. This is volume here, what we're about to compute. All right, so let's look at this example here first. Okay, so here it wants us to, let's see. So it wants us to do a Riemann sum for this integral here with m and n equal to 2 over this rectangle here. All right, so first, and it wants me to use sample, use the upper left points. Okay, or upper left corner, sorry. Okay, let me draw a picture of what this is talking about first so I can at least get the points correct that I'm about to use. All right. So imagine this is 0, 1, going that way. That's corresponding to that interval. The other one would be 0, 2. All right, and it wants m and n equal to 2. That's the number of rectangles. So that would be, like, cut it here. You'd have an interval 1 and 2. And then similarly coming up that y-axis, you have cutting it here so that I have 1 and 2. All right, let me put these points on there a little bit better since we're in R2. So this is the point, run 1, rise 0. That point right there is 0, 0. That point right there is run 0, rise 2. And this point right here would be run 1, rise 2. Okay, now, okay, so what are the upper left corners, that the points that I'm about to have to use on this? Okay, so that's talking about use this point because it's the upper left corner of this rectangle here. Of this rectangle, you're going to use that point. Of this rectangle, this point. And of, you know what? I'm doing upper right corners. So let's change the problem to upper right corners. Just because I had to get upper right. Okay. And then I'm going to use this one right here. All right, upper right corners. All right, if it said upper left, you do the same thing. You're just going to choose the other ones. All right, I'm doing upper right because I've already started this, and that's how it's going to go. Okay, so what are these points? All right, this one right here. So if this is been split up into evenly selected intervals here. So if this is length 1, then to come out here, I'm at 1/2. So then right here, I would be at 1/2, rising 1, because that had to be 1 there. Here I would have been at 1/2, rising to 2. That one, as mentioned, was 1 to 2. This one here is run out 1, 1. Okay, so that's the points I'm going to use. And the function that we're about to plug some of these in, plug this in on, is f of xy is 6 minus 2x minus y. Okay. Now, all right, so what is this integral supposed to equal to? So formally, like what I'm about to do is the integral from 0 to 1, and then 0 to 2 of this function 6 minus 2x minus y. All right, now corresponding to this integral here, dy, because y goes from 0 to 2, dx. Now this is approximately this Riemann sum here. So the sum n equals 1 to 2, the sum m equals 2, or m equals 1 to 2 of, like, f evaluated at these points right here. So let's see, so m n, this is some test point or whatever, x m or y m n. Now multiplied by the area of these things. So like, I'm running out of space on this page here, but like right here you would have xn minus xn minus 1, yn minus yn, m minus 1. Alright, so don't worry about this technical thing. Like, here's how this all breaks open really easy. I just was like writing it just for like what it's supposed to be. This is actually super simple what this is. So this is actually equal to All right, so f at that point right there, like let me call these little like little rectangles. So say that thing has area 1 for that first rectangle. This rectangle has area 2. This rectangle area 3. That rectangle area 4, and they all have the same area. Each one has length 1/2, height 1. So 1/2 times 1. They all have area 1/2. So that when I'm computing this, so going after this first one, I'd have to come up with f of 1/2, 1, because that's that point right there, multiplied by the area of that rectangle, plus f of, doing that one, 1 times area 2, plus f of, right there, f of 1/2, 2 times the third area, plus f of 1, 2 times the fourth area. So actually, it's like now it's going to be just that simple. Now, how do you get these? You're going to take these points 1/2 and 1, plug that into what f is. It's like where there's x, you're going to put 1/2. Where there's y, you're going to put 1. So when you do that, you're about to have 6 minus 2 times 1/2, which is 1, and then minus 1. Then that gives you 4. So that's 4. That area, as mentioned, is 1/2. Length times height. Now I plug 1, 1 into that. So 6 minus 2 times 1 minus 1. Then I get 3. And then times 1/2. When I plug 1/2 into there, x is 1/2, y is 2. I also get 3. Alright, then 2 for whenever I plug in 1 and 2, and still 1/2. Then when you tally all this up, you're going to get 6. So, end answer 6 for using, if I'm using the upper right corners, which it did say left, but I messed it up, so I just went with it. Like, so that's the upper right corner. Upper left corner should have been that one right there, but it's the same computation, just you're going to be plugging in those points instead. Okay. Now, so for midpoint, you're going to do the same thing, and I'm just going to like set it, like, because at part B it says use the midpoint. So I'm just going to like set it up, and then you'll see exactly how it would play out. Okay, so let me draw, so you start with drawing this square first to get these points on there. Alright, put this on here. Alright, so this is 1, 0, 0, 0, 0, 2, and 1, 2. Still, it wants m and n equal to 2, so the picture's the same. But it wants you, when you're choosing midpoints, it wants you to choose the point that's like dead in the middle. Alright. So in this situation, and so this is still 1/2 if you were to go out that way, and that's 1. So the points you're going to have to choose on this one right here, this is going to, you have to come out here midway, which is going to be 1/4. And then coming up here, it's 1/2. So that point is 1/4, 1/2. This point here is 1/4 coming out that way. And then I'd have to go 3, like 1.5 or 3.5. And then here, this is going to be coming out 3/4, rising up 1/2. Here it's running out 3/4, and then rising up 3/2. Alright, so that now that when you do this, you're going to get this double integral from 0 to 1, 0 to 2, 6 minus 2x minus y dy dx, alright, is approximately, alright, so plugging in these points, and all these things also still similarly have area 1/2. You would have f of 1/4, 1/2 times this area, which that thing has area 1/2, and then another one here, here, and here, plus then you do f at that point, times that area, f at that point times that area, f at that point times this area. So all of them. And then there's only 4, but just to save time, I think you get the idea. Area 4, and then you're going to plug 1/4 and 1/2 into here. The 4th goes here, the 1/2 goes there. And then just jump into the end. At the end of the day, it's you'll get 16/2 or 8. But the main thing is that you just get the idea of what's happening, because then eventually you want to move on to like not necessarily doing it this way, but actually computing the integrals for real. This is good for doing like approximations. Like you can imagine, like in Calc 2, there was like trapezoid rule, Simpson's rule, all that kind of stuff. There's all that kind of stuff here for like, so say integrals that you could not compute by like any kind of method. But whereas like something real simple like this thing right here, this like that's just a polynomial in 2 variables. You'll see that can be computed in just practically instantly. But for like really complicated ones, you cannot compute them, so you have to do some kind of approximation. But so that's the warm up. So now let's get to actually computing some of these. All right. And so what about, so I guess before getting into that technical stuff, any functions that's continuous, it's integrable, and like you can relax that to bounded. Most of these problems, you're not going to have to ever worry about it. If you go on, that's sort of like the nature of the game. Is the function integrable, and what can you do about it, and all this other stuff. And once you have this continuity, you can switch the order of integration. So like on those integrals, like let me just show you back on it. Like the way I had it written, I was writing dy dx. That's a polynomial 6 minus 2x minus y. So anytime you have something continuous, you could switch it if you need to do the integration with respect to x first. Sometimes that's like a good thing to do if you have something real complicated that you need to cancel something out. But otherwise, just kind of go for how it's written and see what happens. So let's just go for it. Alright, so here's this integral, that same one that we were messing with before. Alright, so when you're doing the integration, just like how differentiation worked when we had multiple variables, you're going to treat, so I'm integrating with respect to y, you want to treat x as a constant. So what do I mean by that? So first, leave the outside integral alone, 0 to 1. Alright, now I'm going after this inside integral here. Okay, so if I'm doing the integral of 6 with respect to y, I'm going to pick up 6y. Now minus 2 times, so x is a constant, times y. Because 2x is like a constant with respect to y. Now minus the integral of y, which is y squared over 2. Now you have to evaluate this from 0 to 2. And then on the outside, I've got the integral dx. Alright. So, now I'm going to plug 2 into this, so I leave the outside integral alone. So 6 times 2 minus 2x times 2 minus 2 squared over 2. And then you formally got to plugging in 0 into that thing. They're all going to be 0, but just so you could see it, like 6 times 0 plus 2x times 0 minus 0 squared over 2. And all this is dx still on the outside. Alright, so here, so those are all 0. What happens out of all these things? Here I'm about to have, that is 12. And then here I've got 4. So that's going to be 10. So this tallies up as integral 0 to 1 of 10 minus 4x dx. Now I'm back to a Calc 1 integral. So antiderivative is 10x minus 4x squared over 2. You have to evaluate from 0 to 1. Alright, when you plug in 1 in this thing, you're going to get 10 minus 2, which is 8. Then when you plug in 0 into it, because they both have x's, you get 0. So end answer is 8. So you just do them one at a time, like they would call it like an iterated integral. So you come from the inside and then work your way out. All right, let's look at another one here. Okay, so now you have integral of, move this in. So it's x cubed y squared dy dx. All right, so, okay, so this is equal to, so I leave the outside integral alone, 0 to 2. The inner integral, integrating with respect to y, x is a constant. The integral with respect to y is y cubed over 3. That has to be evaluated from 3 to 6. Dx is on the outside. All right, 0 to 2. So leaving the x alone, it's now 6 cubed over 3 minus 3 cubed over 3. So just some number, which if you add that thing up, it equals 63. All right, so that now we're just now at a Calc 1 integral, so that's 63. I would move that to the front because it's a constant. 0 to 2 x cubed dx. Antiderivative is x to the 4th over 4. So 64 times x to the 4th over 4 from 0 to 2. You plug the 2 into there. This thing tallies as 4. End answer 252. All right. Now, more examples here. Okay, so now you have integral of x times cosine of x. So now it's just been written in a different way. So this way it's been written so that like R is that region that's a rectangle on the xy plane, and they've just written it a little bit fancier. Okay, so but the method goes just as before, and I'm just going to write it as an iterated integral. So I'm going to write this thing is equal to integral 0 to pi, 0 to from 1 to 2 x cosine of xy. Now I have to, the main thing is put the differentials in the right spot. So this one is dy and then dx on the outside. So okay, now everything's set up. Antiderivative of this thing with respect to y. Alright, so antiderivative, so and I want, like, that's a constant, so I don't want to really think about that. But the antiderivative of cosine of x times y would be sine of xy divided by x. So let me write this 0 to pi, leave that x alone. Antiderivative of this thing right here is sine of xy divided by y. So I'd be doing a chain, divided by x, doing a chain rule of this integral right here, because x is a constant. Alright, that thing has to be evaluated from 1 to 2. On the outside, I still have dx that I got to deal with. Alright, here, luckily these x's cancel. Integral from 0 to pi, now of sine of 2x minus sine of x dx. Alright, now we just got two Calc 1 integrals. Alright, so this is equal to, antiderivative for sine of 2x is negative cosine of 2x divided by 2. That thing's antiderivative is negative cosine, so, and there's a negative, so it would cancel it out. So plus cosine of x. You need to evaluate from 0 to pi. So then you'd first plug in pi in this thing, then subtract off what you would get if you plugged in 0 in this, And then at the end, so now just like skipping a little bit because we're like into Calc 1 type little computations, you're going to get -2 out of this. All right, let's see another couple examples here. Okay, so now something more complicated here in which you're trying to get the volume of some kind of surface which is trapped in between some functions. Okay, so first let's try and figure out what in the world's going on here. So volume of the solid in the first octant bounded by this cylinder and this plane. So first, what is the setup like that we're about to have? Like, what are the limits of integration? Like, that's the whole big picture. So let me think about like, what does this cylinder look like in R3? So if you were to draw this cylinder, I'll get a extra sheet of paper here. Okay. So I want to draw, what does this surface look like? Z equals 9 minus x squared. Okay. So there's no parameter on y, or no restriction on y. That means y is about to run from -infinity to infinity. When z is 0, x is about to be plus and minus 3 on this. So you'd have so run out 3, rise to go down that way 0, go up 0. Here -3, 0, 0. All right, now up to the top. When x is 0, z is 9. So up here you'd have 0, 0, 9. You've got this type circle here, and the cylinder would be this infinite type of thing right here, going like that. So so that's at least what this function is. What is the first octant? That's being here in this situation here. So stay x positive, y positive, and z positive. All right. Now, in the further last thing, it says it wants me to cut this by the plane y equals 4. So that would be like, imagine come out here somewhere to 4. All right, and just cut this straight up. All right, if you were to cut this thing, what you'd be looking at after you've cut it is, let me go back over to here now. If you were to cut this, you'd be looking at something like, let's see here, because I'm in first octant, some type of little sliver thing like this. All right, this point right here is going to be run 0, 0, 4, because that's the y-axis. So imagine, just to give it a little more setting, x, y, z. This point right here on the z-axis was 0, 0, 9. Right there, that's the origin. Right here, this is run 3, 0, 0. All right, so that's what we want to compute the volume of, that little piece. Okay, so, and the 4 does not go there. 4 goes right here. Sorry about that. All right, now, what is this integral going to be? All right, the integral has to, so this is the surface is this thing. All right, so the integral is going to, so double integral. All right, and of the surface, which is 9 minus x squared. Okay, now, doesn't matter which one of these I do. I'm just for sake of doing it different, I'm going to do dx first. Dx. X ran from 0 to 3. All right, then y runs from 0 to 4. All right, and then so that's your double integral that you'd have to compute. Yep. So, and then you would compute it exactly the same way as like the ones that on the previous one. So I'm going to skip that one because it is exactly the same at this point. So first, so I'll just maybe write the antiderivative for the first one, and then everything is the same. So antiderivative of this is 9x minus x cubed over 3. Evaluate from 0 to 3. Dy, you're going to get some number out of this. Actually, like, let's just finish this up. It's going to go fast. You're going to get some number. All right. There, after this is all said and done, there is no variable of y in this. All right. So then, since there's no variable of y, what you're going to do is just the integral of this, like whatever this number is going to times the length of this interval, which is 4. So end answer, like before cleaning this all up, is 9 times 3 minus 3 cubed over 3 minus that thing plugged in with zeros everywhere, which is just 0. All right. Now, the outer integral is 0 to 4. Some number is just because there's no more y's, it's just 4 times that number. 4 times 9 times 3 minus 3 cubed over 3. Yep, so again, at the end, I guess, clean this up, what are you looking at? 27, or 72, 72. Okay, let's look at, now, a little more interesting integral. Okay, so, first, before going after this, let me say a little bit about like what this function is, like to make this a little bit simpler. Okay, so let's look at, let me write it a little bigger. So you have just this function is the main one I want to stare at. X plus y squared, or e to the x plus y, e to the x plus y squared. Okay, this is the same as e to the x times e to the y squared. Bases are the same. I can add the exponents. All right, so now what I'm about to do is when I write this integral, I'm going to write this integral like double integral, and I'm just going to put these on there. It doesn't matter. I'll do like y first. Well, first let me write the function. So y times e to the x plus y squared. So times x e to the y squared. Then dy, y goes from 1 to 2. dx, x goes from 0 to 1. Okay, now why am I doing like separating that thing like this? Because at this point when I'm doing this integral, x is a constant. So this is, and like if x is a constant, all right, what I'm looking at is this 1 to 2 y times e to the y squared dy dx. Okay, so this integral here, that's a Calc 1 integral with the u substitution of u equals y squared. So you do u equals y squared. du is 2y dy. You'll finish this thing off. Maybe we'll do it right now, I guess. So if I'm about to do this, limits of integration are going to change. 1, whenever y is 1, u is going to be 1. Whenever y is 2, u is going to be 4. Okay, I'll write that on the next line. But like now what I want to do though is like no matter what's going to happen out of this, there's not going to be any x's left, so that like what's going to happen is like this is going to produce just a number. All right, and then that number is going to be multiplied by this integral of integral from 0 to 1 e to the x dx. All right, this number that we just, like before going a little further, like it's going to be 1 to 4 of a 1/2 comes out from this u substitution. That y cancels, e to the u du. All right, now one last line. So integral of e to the x is just itself. So for the first integral, so this is multiplying upon there. So you cannot always split these, like how this split. Like basically what I did was like almost like a factoring of an integral. So this hardly ever works with these exponentials, since multiplying them, if their bases are the same as adding in their exponents. In this setting, you could do it by like just be real careful doing this. Like it only works in very certain situations. So answer for the antiderivative is e to the x. Then when you evaluate it, you're going to have e minus e evaluated at 0, which is 1. Now on the back, I got that 1/2, and then I'm about to have e to the 4 minus e. So that's the end answer for that one. So that's the beginning of all the multiple integration. And if you have any questions, please contact me, and we can set up a collaborate meeting through D2L or any other way. And that's it. I hope you have a good day. Thank you.